So we just talked about looking at the sampling distribution of the sample means for a normal population. What about a non-normal population? Let's take a look. So the data here in the table represents the probability distribution for the number of people living in households. So here are the number of people that live in a household. Say your household has just one or two people live there, three, dot, 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 all the way up to a household of 10 people. And given with this table is the corresponding proportion. So it looks like a household of one is about just under 15% of the population. Households of two is pretty high with about 36%, and so on. So from the table, we can get both the mean and the standard deviation for the number of people living in a household. And we find the mean to be 2.9 and the standard deviation to be 1.48. Problem is, we're not working with a normal distribution. We're actually looking at random variable that is discrete. So we have something that looks like this here. Number of people in a household we know is not continuous. So we do not have normality. I mean, we got this skewed right situation here. What can we do? So we're being asked to approximate the sampling distribution of the sample mean X bar by obtaining, and we're going to do it through simulation. So you know, using technology to simulate this for me. 1,000 samples of size first 4, then size 10, and then size 30 from the population. So let's see how this is done. Okay, this slide that I'm on right now is just kind of a breakdown of the slide to come. So I'll explain it for you. So what's happening here is, here's the table we saw in table 1. Here's the number of people that could be in your household with their corresponding proportions. Then here are all our different samples. So in our first sample, we see that we take a sample of 4, and that first household has 4 people. And then the next 3 households in that sample have 2, 2, and 2 people. So this is sample 1. Sample 1. This is sample 2. And now this table was kind of just dropped in here, right? Just so we can recall what we were looking at. So my rows for sample 1, sample 2, sample 3 obviously only correspond to these columns, C3 through C6, because I'm looking at a sample of 4. So I have all these different samples of 4 here. And from each sample of 4, I can find its mean. So when we look at the first histogram of this, we see that we have out of 1,000 samples. So we're going to look at how does the graph show what the mean looks like? How are the means distributed from these 1,000 samples? And remember, this is for samples of size 4. It's still a little skewed right? It still seems to be somewhat skewed right. So the mean is 2.9. The standard deviation is 0.76. Remember, we're still talking about the distribution of the sample means. So the good thing is that the mean of the X bars does still equal the mean of the population. And the standard deviation of the 1,000 samples for X bar, sigma X bar is just 0.74. So they're close. But what if now I changed my sample size to 10? So instead of taking samples of size 4, like we did here, say we repeated this process and made another chart, but instead we took samples of size 10. Well, as you would expect, this becomes less skewed right. We're getting a little bit more normal. In fact, the means don't change. They're still the same. The mean of the X bars is still um, the same as the mean of the population, mu. And the standard deviation for the 1,000 samples of size 10 is now 0.47. So it's decreasing. It was like what, 0.74? Now it's decreasing. So we're decreasing that spread. And again, we can repeat this process but say, well, now I'm going to take size 30 samples. So now for every sample, I'm going to look at 30 different households and say how many people live in each of your households. And again, nothing happens with the mean stays the same, but the standard deviation decreases. So we looked at a distribution that was not normal to begin with at all. But here's what we can take home. The mean of the sampling distribution of the sample mean is equal to the mean of the underlying population. Whatever that underlying population is, it came at us and it was not normal to begin with. However, the sampling distribution of the sample means will have the same mean as the sampling distribution of whatever that underlying distribution is. The standard deviation of the sampling distribution of the sample means is still this sigma over square root n, regardless of the size of the sample. But what happens is that we watch this decrease. This starts to decrease its value as n goes up. The shape of the distribution of the sample mean does become approximately normal as the sample size n increases, no matter what shape we started with. So keep in mind, we're still talking about the distribution of our sample means. What happens is we may start with something that doesn't look like this at all. We started with something that looked like that. But as we increased our sample size n, we saw it become more bell-shaped, and at the same time, we saw that spread decrease, which would mean we'd get a little bit more of a steeper curve. So the central limit theorem actually tells us that exactly, that regardless of the shape of the underlying population, the sampling distribution of X bar of the means, the sample means, does become approximately normal as the sample size n increases. But how large does that sample size need to be, right? Before we could actually say, okay, the sampling distribution of X bar is normal. Well, it obviously would depend on the shape of the distribution of what we're starting with for that underlying population. If we're starting with something that's highly skewed, we're obviously going to need a larger sample size. So let's take a look here. We're talking about household income and of households, and it starts out highly skewed, right? But as we increase our sample size from 4 to 10 to 25, we see that the distribution of the sample means X bar becomes pretty normal. And we would also expect that spread to decrease, right? Which is the standard deviation over square root n. So if the distribution of the population is unknown or not even normal, it's okay because the distribution of the sample mean is approximately normal, provided that the sample size is, here's kind of that rule of thumb, greater than or equal to 30, right? But remember, that is for the sample mean. So we have a distribution. We're looking at the distribution of some population. It's not normal, and that's all right because we can look at the distribution of the sample means and expect it to be approximately normal as long as we have an N for our samples that's greater than or equal to 30. So on this last example, it's weight gain during pregnancy. And it says the mean weight gain during pregnancy for a population is 30 pounds. So here's for our population. It's got a standard deviation of 12.9 pounds. Weight gain during pregnancy is known to be skewed right. So they're telling us off the bat, this is not normal. You're not going to expect a normal symmetrical bell-shaped distribution. But this obstetrician obtains a random sample of 35 low-income patients and determines their mean weight gain during pregnancy is actually 36.2 pounds. And then we're asked if this result is unusual. So the sample is random. That's that first check mark assumption that we need to say, hey, before I even start, is this a random sample? Yes, okay. Also, is the sample size less than 5% of the population size? Well, we can assume yes, because there are at least about, they say, 700 low-income pregnant women in this particular population. So our sample size is actually less than 5%. These are just assumption check marks that we need to make. Because 35 would be less than 35 out of 700 is less than 5%. So let's represent this probability with this curve here. And let's see what we were asking again. 36.2 pounds. So the given mean for the population is this 30. 36.2 pounds would be here. So we're looking at if being 36.2 pounds for this is unusual. Well, in order to find being above 36.2 pounds, right? 36.2 pounds or greater than, we're interested in this little shaded area here, which would be to the right. So we know that when we calculate our z-score and get this statistic here, the z-score, that we need to get the value from our z-chart, but then we're going to have to take one minus because we're not interested in the area to the left. We're interested in the area to the right. So we calculate the z-score because we're talking about means. So we calculate it using sigma x bar. And sigma x bar is given as, again, this sigma divided by the square root of n. And when we go to our z-chart, we find the corresponding area for that z-score. To the left is this value here, this 0.9977. But since we're interested in the area to the right, we need to take 1 minus that to get 0.0023. So this is that area we were interested in. So if the population from which the sample is drawn has a mean weight of 30 pounds, the probability that a random sample of 35 women has a sample mean weight gain of 36.2 pounds or more is 0.002, which means that about 2 samples in 1,000 would result in a sample mean of 36.2 pounds or higher if the population mean is 30 pounds. So what we can conclude is that either the mean weight gain for low-income patients is 30 pounds, and we just happen to select women who on average gained more weight, or also the mean weight gain for low-income patients is more than 30 pounds. So what we need to keep in mind with these interpretations, because they get real lengthy, is that we're always referencing in regards to the situation, right? We're not making an inference here to all. We're saying based off these circumstances I'm telling you, such as when the mean weight gain is 30 pounds and random sample 35 women. then all of these things I'm telling you is what I would conclude. Okay, so it's important to note that we point out everything in context of what we are interpreting. So just to kind of summarize here, when we talk about the distribution of the sample mean, which is the X bars, we know that the center for both normal and non-normal is the same. And what's nice is so is the spread. The spread for both normal and non-normal is the same, except now we have to use sigma X bar, which is sigma over square root n.